and B. Any 2 points defines a straight line. Whether you're in 2 dimensions or 3 dimensions, if you give me 2 points, you have defined a line. The line that joins those 2 points. I need a way to describe this. Now we're used to going in 2 dimensions like this. It has a gradient and a y, what's it called? A y-intercept. But it's hard to do this in 3 dimensions. Where do I put z and how do I link it together? There's another problem with this. How do I describe this line? It has no gradient. It's not possible. This is not a good way. Oh, I went for this. Okay. So we need a better way to describe a line. So what we're going to do is we're going to use vectors. And this is what we're going to say. We're going to say, first take me to A, and then take me to some point along the line, which could be that way or that way. And this is my point P somewhere along that line. So what I'm going to do is I'm going to go, how will I get to point P? Maybe I should ask you, how are you going to get to point P if you only know A and B?
Is it a midpoint?
It doesn't have to be a midpoint, it could be over here, could be back here. P could be anywhere along that line.
Like a scalar multiple?
Some scalar multiple of
B. A to B.
A to B. So first I'm going to go to A. Oh, I should write in my R, shouldn't I? This is the vector I want, the vector that gets me to that point. And I'm going to get to that point by going first to A and then some multiple of AB. That's exactly what I'm going to do. I used a lambda here, Greek letter L. Greek letter L. It doesn't matter. Actually, you know what I should be using? I should be using T, shouldn't I? I'm used to using lambdas, but I'm going to change it to T because the syllabus has a T. I'm going to use the syllabus terminology instead. Your textbook uses lambda, but syllabus says a T, we'll use a T. Still doesn't look quite like what the syllabus says. That's little a, they go T, D. D is my direction vector. It's the vector that tells me the direction of the line. And this will work equally well in 3D. I go to one point on the line and then some multiple of the vector that describes the direction the line is going. And that gets me to any point on that line. And that is the equation in the syllabus. I'll give you some examples. Sometimes, like we had with the parametric equations yesterday, sometimes there's a domain restriction on what t can be. So for example, A might be, let's do it the way they did it, so you can have a look later, 0, 3, and B can be 5, 0. And I want you to describe in vector form the line segment between A and B. Now in this case A is here and B is here. And I want the vector, so I want the line segment in between them. Well, first of all, I need a vector to get here, that's easy. Then I need a direction vector. What's my direction vector? Well, it's just AB. Or if you prefer, little b minus little a. Got to get used to doing that if you're not already. So that's this minus that. Would you prefer a column vector or an IJK?
IJK.
Any other votes?
IJK is fine.
Okay, so this is 5I hat minus 3j hat. That's my direction vector. And then my line segment is described by going first to A, some multiple of 5I hat minus 3j hat. And that's my vector equation of the line. But there are some restrictions. This describes the whole line. I only want the bit between those points. What values of t will get me between those points? One of them's easy. If I just go to A and then don't go anywhere else, t is 0. But what's the value of t when I'm here?
1.
That would be nice, is it?
Probably not.
Is it? How do I work it out? I want the value of t for which this is equal to 5I hat.
Just substitute and rearrange.
What do you get? How go? I'm just going to go, the end point, I want this, I want to go 3j hat plus t, 5I hat minus 3j hat equals 5I hat. That's what I want to solve for t to put my domain restriction in. I was waiting for the moment when Ben realises he was right.
I was right.
Can you see why though?
Yeah.
I want to get rid of this. I need to subtract 3j and add 5i. It's got to be 1. But in an arbitrary case, you might have to actually solve and work out what value of t gets me the section of the line that I actually want. That's the vector equation. How do I make a parametric equation? Maybe I should label that. This is the vector equation. Well, the parametric equation is exactly what we did yesterday. I'm just going to write this with an x coordinate and a y coordinate. So x is 5t and y is 3 minus 3t. See how I got those? The multiple of I hat here is my x coordinate, and the multiple of j hat here is my y coordinate. That is the parametric equation. Parametric equation, actually. Metric equations, plural. If this was three-dimensional, you would have a z equation as well, just like the syllabus says. Each one is going to be something. Here it's 0 plus some multiple of t. It's always just going to be a plain multiple of t because it's a line, it's a linear equation. If this is two-dimensional, it's fairly easy to come up with my y equals mx plus c, my Cartesian equation. I just rearrange for t and substitute. But in 3 dimensions, that's impossible because you can't substitute 3 things at once and come up with one equation. So what we're going to do is rearrange all of these equations for t. And that's going to become our Cartesian equation. So we're going to go, first one says t is x over 5. And the second one's going to say, let's do this carefully, y is 3 minus 3t, which means negative 3t is going to be y minus 3, which means t is going to be negative y plus 3 over 3. Some people would write that as y take 3 over negative 3 in order to write it exactly the same way the syllabus does. These are the same. These things are all equal to t, so we just write them together. X over 5 equals y minus 3 over negative 3. That's my Cartesian equation. I'm writing this because we're going to practice this in 3 dimensions as well. Those are the 3 forms of the line. You have to be comfortable going forward and back between these different representations. Starting with 2 points, you can get a vector equation by doing this. Got your vector equation, it's easy to write parametric equations. Rearrange for the parameter and make them all equal gives you a Cartesian equation. If you have to go back, just write this as equals t and take each piece separately and write as x equals or y equals. And obviously if you've got parametric equations, you're just going to write r is this I hat plus this j hat. Give the 3 forms of the equation of the line between a can be 2, 0, negative 1, and b can be, let's go 1, 2, 3. Why not? Have a go, write me a vector equation, parametric equations. If you need help, by then I'll be doing it to show you how to get the Cartesian equation. I'm going to start with, what's my direction vector? By the way, if you get the points the other way around, you'll get a different equation, but you'll be describing the same line. You'll just be going, go to point B first and then go some multiple of that vector. You'll still be describing the same line, just with slightly different numbers. So if you don't like having a negative I hat, you can just change all the signs of this direction vector. You've got another vector along the line, it doesn't matter. It's exactly the same. Parametric equations, x equals this, y equals this, z equals that. This is my vector equation. These are my parametric equations. Rearrange. Or if you prefer, in order to write it exactly the same as the syllabus says, you can write it like that. It doesn't really matter, you can go 2 minus x over positive 1, doesn't matter. It's exactly the same. I'm going to do 2 steps for this one, let's have a look. 4t equals z plus 1, t is z plus 1, 4. You just make them all equal. x minus 2 over negative 1 is y over 2 is z plus 1 over 4. And that's the Cartesian equation of a line.
How do you plot that?
We don't. How can you plot it? You've only got 2D page. How can you plot a 3D line on a 2D
You
page?
need a 3D axis for it.
So your graphics calculator can plot it. This is the easiest way to put it in your calculator. Some calculators are different though. Some of them you have to describe x and y in terms of z.
How's my graphics calculator plot?
It typically will do exactly what some calculators make you do. If it takes all three, it just gets a value of t from like minus 20 to positive 20, works out what x, y and z are, and then tries to reduce that to a flat display on the screen, depending on the orientation you've set. Some calculators require you to rearrange it so these ones are in terms of z, and then it just picks a value for z and works out where x and y are for that z. You're not going to be asked to plot it though, just think it through, try to imagine things. What if I ask you, maybe I should give you some practice going the other way. That's a Cartesian equation of a line. Write me a parametric equation. We'll see if we can get to a vector equation. How do I do it? Equals t. Take one section at a time. If that's true, then 3t is x plus 1, rearrange for x. If this is true, then 4t is y minus 2, rearrange for y, and do the same for z. Just do one bit at a time. That's equal to t, that's equal to t, that's equal to t. Might even go down instead of across, it would be easier. Let's get t is, no, what am I doing? X for one. Thinking about the form I want the equation to end up in. So my parametric equations are you agree with me? Okay. So then how do I write the vector equation? It's this point, remembering there's a 0 here, plus t times this vector. And you can write it as a column vector if you would rather, or as ij's k's, negative 1, 2, 0, plus t, 3, 4, 2, or you can write it with ij's k, it doesn't matter. Write it in whatever form the original question had. Calculate the angle between the lines x plus 3 on 5 equals 3 minus y on 2 and x minus 4 on negative 7 is y plus 3 on 5. Still two-dimensional, the textbook doesn't push you very hard yet. How do I calculate an angle between two lines? And there is a trick here that you can use, as long as you make sure it's written in the correct form. If I'm going to work out the angle between two lines, what I care about is the direction of those lines. The direction is given by the direction vector. Have a look back here. The direction vector was 3, 4, 2. Where is 3, 4, 2 in my original Cartesian equation?
Where T is. Yeah.
It's on the bottom.
Oh, I'm doing a parametric,
Yeah, yeah. I want to look here because that's what I've got here.
Yeah.
Right? The direction vector is the denominator. As long as you have always written positive x, positive y, positive z. So if you write it like this one, you're going to go wrong. This one should have a positive y to make that work, so this is actually negative 2. So direction vector of line 1 is 5i hat minus 2j hat. You can read it straight off the equation, because that's what you're going to get if you try to do all this. I'm looking for the multiple of t, because the multiple of t here gives me the direction of the line. And the direction vector for line 2, actually that's a vector, sorry, vector for line 2 is positive x, positive y, negative 7, 5. Now I've got the direction vectors. How do I calculate an angle? You all did this yesterday.
We did.
You did. Do you remember what you did?
Maybe.
I think Rain remembers, but I think you might be the only one in the room who remembers. How do I work out direction? How do I work out an angle between two lines?
Yesterday.
Yes, yesterday. Oh, it is right there on the screen. Oh no, it's not. That's a cross product. I want the dot product. Where's my dot product?
Oh, I remember how to do it.
Now you remember? Okay. Cos theta is d1 dot d2.
This wasn't yesterday.
Wasn't it yesterday?
No.
Was it the end of last week?
Yesterday
Yeah.
was parametric.
I thought there was one question I asked you to find.
No.
Oh, must be. Okay, end of last week then. Sorry. There you go. Length of d1, length of d2. Off you go. Work out the angle. d1 dot d2, so you're just going to go 5 times negative 7, and then 2 times 5, minus 10. $25 plus 4 is 29, that's pretty bad. 49 plus 25.
74.
50 plus 25, yeah, 74. 75, so that's 74. Negative 45 over, frankly I don't care because I'm just going to get my calculator and work out theta. Inverse cos of that.
Choose
What is it?
166.26.
Beautiful. Now, what else did they say here? Anything else? Oh, thinking about lines in 3D. Oh, man. Okay, now, in 2 dimensions, you can have lines that are parallel or that intersect. In 2 dimensions, if they're not parallel, they're going to intersect. That is not true in 3 dimensions. Ryan, we've chatted about this already.
Because it looks like it could intersect. It could be like whatever.
These 2 lines are not parallel, but they're
Yeah.
never going, well, I can't even do that with my hands. They're never going to meet each
Because you
other.
then have that z-axis.
Correct. You have a z-axis to move them apart. This situation is called skew. They're not parallel, they're not intersecting. They're skew lines. S-K-E-W. So sometimes you might have a look at things and go, do these lines actually intersect? If so, you can find the point. If they don't intersect, well, they might be parallel, but they might just be skew. And a reminder, if you need to figure out whether two lines are parallel, what do?
Scalar.
So you look again, you look for the direction vectors first, and then ask, is one a scalar multiple of the other? Then they're parallel. If it's three-dimensional and they're not scalar multiples, they might still not intersect. If I want to find out whether two lines are perpendicular, realise this is perpendicular, so is that, so is that, so is that. All of those things are all perpendicular. There's an infinite number of lines perpendicular to a given line in 3 dimensions.